So, hi, I'm Alex, and I'm in my second year of my PhD. I work mostly with social media data to identify sort of actionable information for emergency services. So, as crises and disasters are sort of ongoing, to highlight that, and in time, if there's any useful data for public health bodies, certain organisations, emergency response, that sort of thing. And really, I'm just going to be giving a kind of overview of the tools that I've been using in my research, the sort of the techniques that I used in explainability, and to discuss basically how it's used, different use cases and limitations and that kind of thing. So how do we actually define interpretability and what is involved in the interpretation of neural networks? So interpret means to explain or to present in understandable terms, to convey or otherwise visualize the sort of inner workings, the internals and decision making in neural models. Often we explain the results of our models with sort of evaluation metrics like post hoc, but being able to further convey why a model may arrive at a particular prediction in a more sort of human readable, understandable, visualizable manner can help facilitate better data collection techniques and architectural decisions, and provide deeper insight into how our models operate. So interpretability allows us to answer such questions as, what does my model perform poorly on? Why did my model arrive at this particular conclusion? Is its behavior predictable such that if I was to change the grammar or the tense, would it arrive at a consistently predictable conclusion? So despite being a sort of newer, well, I say newer, despite there being a bigger surge recently in interpretability and machine learning, there's a variety of techniques available to interpret neural models, and particularly neural language models. So I work mostly with text, so forgive me if I kind of skip over a lot of the kind of image-based work, but I do try to cover it a little bit. So you have, there's a number of different techniques. You have attribution-based explanations, which allow us to assess what the sort of dominant features were that contributed to a particular prediction. Various algorithms can assign a sort of importance score to each given input feature, effectively summarize and visualize these scores at the sort of input level. There's also ways to show kind of activity at a neuron level, a layer level. There's also feature ablation techniques, so we can like substitute segments of an input document with different tokens to measure their effect on prediction. So to scramble the input sequence to assess the effect of, say, word order, to maybe translate an input sequence to and from a source and target language in machine translation, sort of measure its capability to maintain grammar, sentence structure, that sort of thing. And we can also visualize the underlying attention mechanisms present in some architectures, such as popular ones for language, such as transformers and BERT, and yeah, to visualize a sort of layer by layer attention mechanisms to assess which tokens in a sequence are sort of taken most into consideration during training. So interpretability techniques exist for a variety of applications, some of which might be of kind of greater use to you outside of strictly of text classification. There have been significant works in interpretability for image classification, I believe way like more so than text. We can use interpretability techniques to compute the strongest sort of attributions for a particular image. As you can see in the example, they're sort of like identifying, how to classify a swan, I'm guessing. So visualize the sort of most important pixels for that model to reach a particular decision. We also have text generation, so we can use interpretability techniques to allow us to form a deeper understanding of the linguistic properties that a model may be failing to learn. So like I said before, sort of if your model's been trained on significant instances of, say, poor grammar, then we can examine maybe that's what kind of detrimental effect that has on text generation, which may improve data cleaning techniques, collection techniques, that sort of thing. And with the example on the right, we can also visualize the strength of a model's ability to resolve co-referencing expressions in a document, sort of pronouns to their nouns, and lead us to a deeper understanding of the kind of syntactic relationships within the model. So lastly, a place which has got a lot of interest for explainability was the domain of recommender systems. So companies such as sort of Spotify seek to provide both users and their researchers with sort of richer explanations of why something's been recommended. Is it like a certain playlist you've listened to, a certain podcast? Maybe it's like a certain mood that you go to. They have playlists for that. So which then influences how they design their recommender systems. So what tools actually exist that employ these techniques? So since the start of, I would say, last year, I've explored a sort of number of interpretability techniques for crisis disaster for classification. Some of the tools listed often sort of contain the algorithms of others. There seems to be a lot of kind of collaboration and cooperation within the community, at least from the text-based side of things in research. But out of these, I'll focus on the ones which I've kind of used quite extensively, which is Lime, as Yola went over, Google's language interpretability tool, and PyTorch's, so yeah, Facebook's Captum, which I explored at a bit, probably the deepest level out of a lot of them. So LIME stands for Local Interpretable Model Agnostic Explanations, and is an algorithm which can be used to kind of explain a variety of different classification processes. So as the name suggests, it's model agnostic and therefore widely used in interpretability research all across the board. It only really relies on some sort of kind of, sort of NumPy input sequence and then a predictive function at the other end that outputs some sort of probabilities for its functionality. So as Yola spoke about, it works by generating sort of, slightly different versions of an input sequence and predicts the sort of the outcome of all these kind of permuted observations, and then it compares it to the original observation by some sort of similarity score, selecting sort of the best features to describe the input sequence, and then extracting the weights, explain local behavior, that sort of thing. So LIME can be used to highlight the efficiency or shortcomings of any particular model. It can work on a variety of different inputs. So as you can see in, figure 1, it can be used to highlight what the model closely pays attention to with, the labels electric guitar, acoustic guitar, or Labrador. In figure 2, we can see with text the feature attributions of sort of game reviews by the sort of sentiment expressed in the sentences, which kind of helps explain the model's understanding of the reviews. Another tool we investigated was the language interpretability tool, or LIT, developed by Google. So it's more of a GUI-based approach to feature attribution. It's really useful if you want to compare sort of different documents with each other. You can just do it side by side and see how different features are kind of have a different effect on each other. So LIT allows us to compare input sequences, their attributions, project the sort of embeddings to PCA or UMAP. It allows us to directly edit input sequences, run subsequent predictions on that edited sequence. It allows us to generate counterfactuals, so like word replacement, scrambling the input sequence, or back translation, so like to and from a source and target language. We can also generate sort of confusion matrices, see where we got things right, see where we got things wrong, and even kind of, and it even lets you on the bottom here analyzes, this is particularly for transformer models with an attention mechanism. You can see the what the model pays attention to at each particular layer. So through LIT, we actually managed to identify quite a lot of irregularities in the data set that we were using. with respect to incorrectly labelled location information, which ended up in sort of muddying our classifiers results, not recognising particular instances of location-based text, which I'll get onto in a wee bit. So all in all, kind of a very useful tool. There are some limitations. It's not very good for scale. It's not very good for scale at all. Actually, the authors actually conceded this in the paper themselves. It doesn't really work well with data sets past sort of 10,000 samples in size. So it's only like if it's good as a sort of quick snapshot if you can a brief analysis into the explainable sort of parts of the model. So it's useful for that. The tool we found the most useful and effective was Captum. So this is the one that's developed by the PyTorch team, and it provides a much more sort of complete collection of interpretability techniques. It's not just like an overview. It's not just, oh, let's look at the feature attributions or sort of saliency maps. It's you've got layer by layer importance. You've got sort of neuron attributions. There's quite a lot in there that I've barely touched upon, and it even provides multi-GPU support. So like parallelizing a lot of your processes, which is really good. One thing I would say, I did find it sort of personally not as straightforward. A lot of the processes are sort of laid bare, so they are, like if you were to use a library such as like Hugging Face to train things, you're kind of used to just setting up trainer, a few parameters and on you go. Whereas this is, you're connecting to certain things and you need to unconnect hooks and all this kind of. It was a bit of a nightmare to set up. But once you kind of get going, you start understanding things, and it gets you a kind of deeper understanding of what you're actually doing with your with the methods, which is also a plus. So actually moving on to how I use this in my kind of recent work and a sort of work in progress, a journal paper that we're working on. So within the domain of crisis and disaster classification. So yeah, for the last few months, I've been working on a project identifying social media content that's considered actionable, important to emergency services, public health bodies, funded by a research initiative known as the Trek Incident Streams Track. It's partially funded by US government agency NIST and a few other people. So through this research initiative, it was found that around sort of 10% of information posted on social media during crises can be considered immediately sort of actionable by these interested parties, but we don't really have the tools at the moment to sort of immediately identify that information and categorize it. And obviously you can imagine if there's all these tweets coming in about a certain crisis or disaster, that it's completely impossible to do manually. It'd be too overwhelming. You've got tens of thousands per second. So the Trek Incident Streams track tries to set this up as a sort of multi-label categorization approach, where you have you have stuff like, oh, is it a location? Is it like, is there multimedia present? That sort of thing. But obviously there's that's a whole kind of research direction in itself. Multi-label classification is, kind of historically, you don't tend to get great evaluation scores for, you don't get great results for. So there's a lot of facets to consider in designing a model for this kind of thing. So in order to categorize this information, sort of care must be taken in designing the ontology. It's also relying on a sort of relative cohesion amongst sort of manual assessors labeling things sort of the same way, particularly in the track itself. It has about 25. Yeah, there's 25 categories that it's meant to be assigned into. So you can imagine that getting a bunch of different assessors to agree on, what a certain, 140, 240 character document is talking about is well, never happens. So there's a lot of factors which can affect the model's capability to correctly classify this information. So by using interpretability techniques, we were able to identify where our model was failing to learn from examples and why. So for instance, on the right, we examine the property of whether a document contains a mention of a location-based entity or not. So our model is pretty confident that California represents a location. So it's a really strong attribution towards the positive class being, like, is it a location or is it not? However, we found that on documents which contain the token Baltimore are classified, or found it particularly difficult to determine whether or not this was relevant to the task. So on closer inspection, we found that a significant amount of documents containing Baltimore were marked as irrelevant. So the way that the assessment labeling process was set up is that if you mark something as irrelevant, you can't label it anything else because it's just deemed irrelevant. So over time, if you're passing that through a classifier, it's just learned to associate Baltimore with irrelevant documents and therefore not location. So we managed to identify quite a significant number of documents labelled as irrelevant that may have been hindering not just ours, but participants in the research track's ability to categorise that information. So moreover, tools such as Captum allows us to inspect a sort of layer by layer attributions across certain tasks. So if you've got like a model like BERT transformer architectures as a base, it contains 12 hidden layers, which each layer is arguably responsible for learning particular linguistic properties. And we were able to analyze what tokens our classifier paid attention to and kind of what stage of learning. So in the figure shown, each row represents a single task and each column represents a different document. So we have the tasks, multimedia share, move people, and emerging threats. So, is this document, does it have an image or a clip associated with it? Is it talking about a particular image or clip? Is this document describing a request to evacuate people? Does this document describe an emerging threat, a crisis or disaster that's just occurred? So from this, we can see, for instance, that multimedia share identifies tokens such as pictures, live, video is quite strongly, indicative of that is the case. We're talking about an image or a clip there. Move people similarly identifies tokens such as ordered, advised, evacuation, alert. Emerging threats, you've got earthquake, storm, warning, earthquake again, near. So without interpretability, we would know that, this is why our classifiers perform correctly. It could be some sort of, it's likely not to be, but it could be if a label is poorly designed, that it's some sort of fluke that it's classifying a lot of things correctly because, maybe there's some sort of ultra helpful token which isn't directly relatable to the label itself, but helpful. So in our case, the main limitation though was identifying actionable information in sort of categories for where there's a lack of data. So it's quite easy to identify tokens or identify documents rather, where there's locations or expressions of sentiment or is there multimedia in it, because the picture or image or video, those kind of tokens pop up all the time. But it was much harder to identify sort of emerging threats or search and rescue operations that were happening, which is the ones that we actually care about. So as such, we decided to sort of examine whether it was possible to alleviate that sort of poor classifier capability using sort of transfer learning techniques between tasks. So under the assumption that tasks that were highly co-occurrent in the data set, we assumed that must mean they were somewhat relevant. So we were analysing the effect of transferring sort of between those labels. We got quite interesting results. In the figure shown, our columns represent two tasks trained in isolation, and then the third column is those tasks combined sort of in succession. So we can see from the first example that a classifier is sort of all over the place. It doesn't know where to look, and it ultimately decides that this document isn't about an emerging threat. It's fairly confident that identifies the the token video as representative of sort of multimedia entity. And then strangely, the combination of the two causes it to sort of hyper focus on video, also sort of strengthens the attribution of here, which is, also related to multimedia. So it almost cancels out the noise from the source task, which is quite interesting. So you would expect them to have to be sort of really mutually helpful, as in they're both positive towards the positive class, but it seemed to be sort of, it's found the sort of antithesis of itself, I guess, from the source task. For the second one, for location and move people, we can see that stuff like Louisiana, Louisiana and evacuation, sort of the subtokens for that, is learned together, evacuations in order, then move people, and then you can see that that sort of strengthens the confidence of the classifier and the confidence of its attributions. We can see a similar effect between multimedia share and emerging threats, sort of the opposite way round. So when we examine the token saliency multimedia share, greater emphasis around the intermediary layers, sort of tsunami, warning, magnitude, earthquake, and rocks, since emerging threats seems to focus on tokens sort of within these ranges, namely sort of warning and earthquake. The combination of the two seems to divert Bert's attention within this range. So it might not necessarily be that it's particular tokens which are helping, but the fact that it's diverting its attention to this place in the initial source task, if that makes sense, to a sort of subsequence of it. But regardless, these are observations that we feel we wouldn't have made without analysing these via interpretability techniques, and it helped us to arrive at a greater understanding of what is our model was actually doing and learning from our data. And as mentioned previously, the information learned from Google's Lit tool, we identified a significant number of tweets which improved not just our data collection approach, but valuable information for the TRACS assessment criteria. So what are some exciting developments in research directions and interpretability? There's significant discussion on how to protect against agents which may manipulate, poison, otherwise attack the process of a neural network. As such, interpretability techniques strive to sort of achieve more trustworthy systems, could effectively help sort of debug a network and identify these tasks before deployment. As the field develops, there's developed a need to define theoretical approaches in interpretability, and research has been made in sort of grounding these concepts mathematically, leading to a more robust and thorough avenue of research for the field. Lastly, since interpretability allows us to probe our models, more work has been produced on model debugging, which is a promising area which would undoubtedly have an enormous impact on the field of machine learning as a whole, as we kind of try to understand the inner mechanisms of the models we're using. So just to, I'm kind of realising the time, but I'm just wrapping up, and just to talk about a number of limitations in current approaches. So as discussed previously, current tools do not scale particularly well to sort of medium or larger data sets. Tools such as Lit are great for analysis of small sample, but kind of struggle to process data sets of a significant size. It's not the biggest deal unless you have a lot of data, I guess, that varies quite a lot. So you would have to try, a lot of different samples and analyze them, and then you wouldn't be able to see the kind of bigger picture. So, I would say that scale is kind of a problem at the moment. Also been working adversarial attacks on gradient-based attributions, which kind of the authors that I've listed there, which I'll link in the chat later on, we are effectively able to sort of manipulate the feature attributions to focus on more irrelevant and misleading items, which overwhelms the gradients, still making the same predictions, but affects the attributions directly. And similarly, I think it was Kindermans and et al. That demonstrate that they can purposely force sort of misleading attributions in the classic image MNIST task. So lastly, explanations generated for models which contain a sort of attention-based component are found to be at times unreliable. Attention weights are often uncorrelated with gradient-based feature attribution scores, and often varying attention patterns can lead to the same prediction and are not necessarily indicative of one prediction or another. So interpretability can provide researchers and machine learning engineers with the ability to describe sort of neural networks in human understandable terms. It's particularly exciting. Each small breakthrough means we're able to address questions that we just couldn't have answered before, because we can examine the model internals. Being able to effectively troubleshoot our models has the opportunity to produce a sort of domino effect throughout machine learning. I hope that I provided some sort of insight into the tools used, outlined some useful use cases, and yeah, I'll be happy to answer any questions that you have for me. So thanks for listening.
Amazing. Thanks for that, Alex. That's really interesting. I just have a quick question on, I guess, your project in general. So the data you take, is that just from Twitter, like tweets?
Yeah, the data is. I can link that in the chat as well. You can play about with it because it's not. It's open to the public, so it's the aim for the incident streams track was to kind of have a standardized data set of just social media like tweets based on. I'm assuming they scrape it on some certain keywords. The whole data collection techniques is outlined in the paper they've got, but it's just Twitter. It's started off as, you know, maybe about 30,000 tweets, but more recent editions of the track, I think it's like something up to about 3 million or so. There's quite a lot of it's quite a substantial data set now, and it's split into an anthology of, like, you know, 25 different things that it could be talking about. So yeah, I can link that in the chat. It's freely available online to use if you want to play about with it.
Yeah, cool. And so when they look at the tweets, what part of the tweets do they look at? Is it just like the words and the hashtags, or does it look at who actually tweeted it as well?
Well,
like, so
that's up to the participants, because you're given, I don't know if you've ever kind of interacted with the Twitter API, but you're given a big JSON dump of the tweet. So you're given, like, you know, here's the username, here's the date it was created, here's the text, was there any images, here's the link to the images. So you've got a lot of metadata there as well that you can use, and it's up to you whether you use it or not. The only restriction I think that the track has is it needs to be for assessment anyway, it needs to be data that was only currently available at the time. So you can't really use stuff like Wikipedia links, because obviously those things are updated constantly. So it's kind of unfair if you're wanting to create an actionable, you know, right at the moment sort of assessment, really. But yeah, you can use a lot of things.
Oh, cool. Okay. Yeah. So I won't soak up too much time. So there's other questions. So we have one from Rory Morrison, which says, this isn't so much to do with explainability, but could this work be extended to try to predict events, not like earthquakes, but perhaps protests or riots?
Yeah, there's been quite a lot of work on that, actually, because a lot of the initial parts of the track were using other data sets, called Crisis Lex, which they obviously, it's in the name, it's crises, but there's also stuff for big riots. I think a lot of them covered like Ferguson and stuff like that from years ago. And then yeah, there's definitely bigger data sets for general events. There's also I know for a fact there's election based stuff, which is quite interesting as well. So yeah, there's quite a varying amount. I'll try to find the link and I'll just add it to the Google Docs that Yola created, and we can all just, there's just a big dump there. So yeah.
Really cool. So second question, do you have, I guess this is just for everybody, do you have any recommended books for newbies in interpretability?
Yeah, actually, I just bought one. Was one that came out, I think it was like a week ago. So I'm not so much a recommendation as in this is great, because I've not properly read it, but it's quite sizable. So if you're wanting to look it up, it's Interpretable Machine Learning with Python, and I'll link that in the Google Doc as well. So that's, yeah, it's like really thick, so it should be somewhat useful at least.
And the link that I just posted in the chat gives an excellent, it's a free, it's just available on GitHub, it's a free book, and it gives an excellent kind of brief overview about all of these models, all these techniques, quite a simple way. I reference it all the time in my PhD. I'll pretty much dedicate my thesis to this man. So yeah.
And everything that you guys have been speaking about today, that can be done. So you've just been doing this on Python, all these tools.
Yeah. Yeah, I don't really work outside of Python, really. I imagine there's probably there's a decent, I mean, there's a sizable community for machine learning in R. I'm assuming there's probably stuff there, but it's not something I could tell you for certain, unfortunately.
I think R has less libraries, but a lot of these techniques you can implement yourself, and therefore it should definitely be possible to do it yourself. Sure. MATLAB has a bunch of, actually, I worked for MATLAB for about 3 months and built a few of these, so MATLAB is great. Go look at MATLAB interpretability techniques, because I made them. Yeah, so they have a bunch of like standard libraries that you can use just out of box. You don't have to do much manipulation, they just kind of give you an explanation, which is kind of cool too.
Amazing. Okay, well, we're about 5 minutes over time, so maybe we'll stop there. But thank you very much, Yola and Alex, and thank you for everyone that's attended. So we'll get these recordings up on the website soon.